Welcome everyone. In this video, we'll learn about angular acceleration and its components. As we know, when a body rotates, it will have angular velocity. The same way, when the angular velocity of a body changes with respect to time, it is experiencing an angular acceleration. That is, rate of change of angular velocity is given as angular acceleration. So same like the tangential velocity which we have used for converting angular into linear, the acceleration also has a linear component known as tangential acceleration. As like the tangential velocity which is given by the formula V is equal to R omega, the tangential acceleration is also given by the formula R alpha, where R is the distance between the axis of rotation and the point about which the acceleration is found, and alpha is the angular acceleration. So from the formula, it is clear that if the alpha, that is the angular acceleration of a body, is 0, then the tangential component of acceleration of the body will be 0. In that case, the body rotates at constant angular velocity as seen in the image. So a rotating body, along with experiencing tangential acceleration, it experiences one more component of acceleration known as radial acceleration. So to understand the radial component of acceleration, let us see about centrifugal force and centripetal force experienced by a body when it is rotating. So the centripetal force is the force that is acting towards the center of rotation. So this centripetal force is responsible for making the body to rotate and also to keep the body in the same path. So this centrifugal force is actually the reaction force that is created due to the inertia of the body, and this will be acting away from the body, that is outwards. Thus, the forces are equal in magnitude and opposite in direction. The magnitude of the forces will be given by the formula F is equal to m omega square r. M is the mass of the body, r is the radius of rotation, and omega is the angular velocity. So according to Newton's law, force is equal to mass into acceleration. So equating this, ma is equal to m omega square r. Cancelling out mass on both the sides, our acceleration will be equal to r omega square. So that will be equal to r into v by r the whole square, which is utilizing the formula v by r from the tangential velocity. So substituting this and simplifying, we'll get r omega square is equal to v square by r. Thus, the radial acceleration will be equal to v square by r. So the formula for radial and tangential accelerations are shown here. At is r alpha and ar is v square by r. Represent the tangential and the radial acceleration in the figure. So the tangential will be always tangential to the link, which is 90°. So if this is the alpha, the tangential direction is given in the figure, and the centrifugal force will be acting away from the body in this direction along the link. The centripetal force will be acting towards the inside, so which is represented here, and the direction of centripetal force gives the direction of radial acceleration. Now to find the net acceleration, use the triangular law of forces, which states if two vectors can be represented in magnitude and direction by two adjacent sides of a triangle, then their resultant is the third side taken in the reverse order. Utilizing that, the radial and the tangential acceleration, which will be always perpendicular to each other, is represented by two sides of a triangle. Then the resultant of this two acceleration will be the net acceleration of a link, which is represented by the third side of the triangle in the reverse direction as shown in the figure.